Hi ladies, today we're going to be talking about chapter 16, section 6, which is our last section of the chapter, and it's about nuclear fission and nuclear fusion. So nuclear fission is essentially when a large nucleus is hit with a super tiny particle. And when I mean small particle, I mean a neutron. And what happens to the nucleus is it splits into smaller nuclei over several actions, and what ends up happening, and the reason we like it, is it gives a large amount of energy that can be released. So if you were to look at this nuclear fusion, we have a neutron bombarding uranium-235, and this unstable nucleus starts to form it starts to split apart and become uranium-236. So it gained that neutron, but it's so unstable it spontaneously breaks apart into krypton and barium-142, as well as 3 neutrons and lots of energy. Now, this is the reason why we love nuclear fission so much. We get out so much energy from this reaction, and we can actually cause it to happen over and over again, and this is called a chain reaction. And this is essentially when a critical mass of uranium undergoes fission, and whenever it undergoes fission, if you take a look back, it's releasing lots and lots of neutrons, which is the same particle that started this entire process. So if you were to look at a nuclear chain reaction, whenever the neutron hits that iridium-235, it causes krypton and barium to form, but then it creates these 3 other neutrons, which then hit other uraniums, and that will cause them to undergo fission as well. And this occurs over and over again, creating large amounts of energy. Now, I'm not concerned that you know that uranium breaks apart into krypton and barium. What I am concerned about is making sure that you can find an unknown in a chemical reaction. So remember, we want to make sure that all of our subscripts total to the same quantity on the reactant side as well as the product side. Same for our subscripts. So on the left side here, we have 1 plus 235 gives us a total of 236 for our mass number, and that's going to equal the total of the right side. And remember, the total on the right side should equal the same number. So we would take our 137 plus our unknown number plus our neutron, but look, there are 2 of them, so that coefficient does come into play. So we have 2 of those neutrons and our energy. We don't have to worry about writing our energy into the equation. Just remember that it does release a lot of it. So once you solve for x, your number should be, we have a total of 97, and remember that this is our mass number. And we will do the exact same thing for the subscript or our atomic numbers. So on the left side, we have 0 plus 92 equals our subscripts, and that would be 52 plus x plus, it is 2 times 0, so that is still going to be 0. And after you subtract away everything from our x, your answer should be 40. So remember that that subscript number, that is going to be the atomic number, and this is what we're going to use on the periodic table to determine the new identity of this nucleus. After looking at the periodic table, you should be able to determine that ZR has this atomic number of 40, and remember, this 97 is something that we can calculate. In nuclear power plants, we have a lot of fission to produce lots and lots of energy, and this is a great way to get a lot of energy. It doesn't create it doesn't take up a lot of space, it doesn't create a lot of air pollution, and so that's why it's been so interesting to study. And what we end up doing is we have control rods in the reactor to absorb extra neutrons and slow down this fission process, because we don't want too much energy being released at once. This is the same type of reaction that is taking place, in whenever we are releasing this energy, it creates so much energy it could go through cement walls. So we want to make sure that we can control this radiation. And the way that we do that is we have control rods and we have the fuel in here. And what it ends up doing is it controls the chemical reaction, releases large amounts of energy, which we use as heat. That heat is going to warm up the water as steam, and then we use turbines, steam turbines, to create lots of electrical energy. We then also remember that we want to cool it down and pump it back in so that we have this reusable process, and it doesn't have a lot of waste at all. Nuclear fusion, on the other hand, is the exact opposite of our nuclear fission. It occurs at extremely high temperatures. So this is the stuff that takes place on the sun. And it's where you have two small nuclei squished together into one larger nuclei. It does release large amounts of energy. However, sometimes it's very difficult to contain. So in nuclear fusion, we have to have a large concrete shield to protect us from that extra radiation. But we do have the ability to harness the steam, like we did previously, to convert it into electrical energy for us to use. So overall, if you look at the difference between nuclear fission and nuclear fusion, you should be able to determine which of the following each one of these categories it fits in. So if a nucleus is splitting, that should be in your nuclear fission. If large amounts of energy are released, that's going to be both of those. Small nuclei are going to form into a larger nuclei. Remember, that's like putting two together, so you're going to fuse things together. That would be number 2, or nuclear fusion. Our hydrogen nuclei react. Once again, that is going to be number 2, so that's really a key difference between the two. And then several neutrons are released. Remember, that's nuclear fission, and that's where we can get our chain reaction to occur. And that's it for today. Have a good one.